Hello everybody, you are welcome to this 9th lecture session on Database Management Systems course. In this session, we will have a look at brief introduction to schema refinement, and then we discuss about functional dependencies and inference rules, which are very important concepts that are used in the process of schema refinement, which is sometimes called as database design. Then we talk about normalization and first and second normal forms. This is going to be the content of this session. All database applications have certain constraints that must hold for the data. These set of constraints help to make the system to accept correct and then valid data. That means when we enforce these constraints, sometimes which are called as integrity constraints, they help us to make the system to accept correct and then valid data. A database management system must provide facilities for defining and enforcing these constraints. The various types of constraints are available, and here we will be considering the following kinds of constraints for relational data model. Domain level constraints, which talks about the data type for the columns or attributes, null or not null, check for the certain range, for the values under certain columns, specific columns, all these things, they come under domain level constraints. Then we have entity constraints like a primary key constraint and unique key constraints, which are imposed at entity level or row level. Then we have referential integrity constraints, which we have already discussed, which is implemented using foreign key in relational data model. So we need to the database management system must provide facilities for defining these kinds of constraints so as to make the system to accept correct and valid data. A good database design practice is essential to develop good relational schemas at logical level. Good database design is needed for the following reasons. First, we will have clarity in understanding the database, and the second is to formulate good queries. That means if we have reasonably good database design, then it helps us in understanding the data contained in the database in a proper way, and which helps us to pose or formulate good queries at the time of retrieving data from the database. This is achieved by schema refinement. This process of achieving good database design, we also call it as schema refinement. It is performed on the conceptual schema, which is the result of mapping high level conceptual schema, that is ER model, to data model specific to conceptual schema, or in this example it is relational schema. That means if we go back and then recall our understanding about the steps, various steps that need to be carried out in database development, first is requirements analysis, then it is conceptual database design, where we will be using ER modeling or UML to get an understanding about the data that is contained in the database, and up to this it is independent of any particular data model or implementation data model. Once the conceptual design is done, that means once we are ready with the ER model, then we need to decide upon the specific database management system or the implementation data model, or we also call it as representational data model, to implement our database. And in our case, we have chosen to go with relational model. Since we have chosen to go with relational model, the conceptual schema, that is high level conceptual schema or high level data model, should be translated into the conceptual schema, which is specific to the data model, that is relational data model, and this part is called as logical database design, and then drawing ER diagram is called as conceptual database design. Okay, now we are focusing on this part, which is called as logical database design, and then once we get this conceptual data model, conceptual schema with respect to the or in the specific data model which we are going to implement, then we need to perform schema refinement. That is, we need to apply some rules and then do something to enhance the quality of the schemas or the tables that have been designed at logical level design of the database, so as to eliminate redundancy and then so as to increase the quality. That is, When we eliminate redundancy, then we are increasing the consistency of the database. We try to eliminate redundancy, and we also try to eliminate the anomalies or undesirable properties in the schema, database schema. Here we focus on that part, that is, we perform schema refinement on conceptual schema which is specific to relational model, that is, we also call it as relational schema. That means when we translate the ER model to conceptual schema which is specific to relational model, we get raw schemas which may not be that refined, and here we perform the schema refinement to achieve better quality of the database or relational schemas. First we need to study about the functional dependencies. Functional dependency is a constraint between two sets of attributes from the database. If a database schema has n attributes, A1, A2 up to AN, then think of it as a universal database schema R, and then you include all the attributes that are available in the database. This is considered as a universal schema or universal relation. For example, in my database, if I have employee table with employee ID, employee name, and then age, and one more table called as department with department number and then department name as the attributes, then for the sake of schema refinement, I can think of a universal relation which I can call it as a company or something, some name I can give, and which will contain the attributes EID, which is union of this and this. That means it contains all the attributes that are available in all the relations of that database. So it will contain EID, ename, age, DNO, and then DName. This imaginary relation, I am calling it as a universal database schema. This is not a real table. Actually, this does not exist in the database, and this is conceptual for developing formal theory of data dependencies. And we need to learn, we will be learning and understanding all the concepts of functional dependencies using and which are applied on this universal relation, universal schema. Coming to functional dependency, which is denoted by X, an arrow mark, X, arrow, Y, and between two sets of attributes. Here X is on the left hand side, Y is on the right hand side, and X could be one attribute or it could be a collection of attributes, Y could be one attribute or it could be more than one attribute, and denoted by X determines Y between two sets of attributes in R and specifies a constraint on the possible tuples that can form a relational instance R of R. That means if you look at a relation instance R which is on R, capital R, which is nothing but the relational schema, and relation instance small r can be thought of as a table, and a functional dependency is denoted by X determines Y, and X could be a set of tuples and Y is X could be set of attributes and Y is also set of attributes. Values of Y component are determined by X component. This meaning, what is the meaning of this? We read it as the values of Y according to this are determined by values of the component X, and otherwise we say that Y is functionally dependent on X. Thus X functionally determines Y in a relation schema R if and only if whenever two tuples of R, that is relation instance of the relation schema R, agree on their X values, they must also agree on their Y values, and Y determines X, that is other way around, is not true. It need not be, sometimes it could be or it may not be. That is why if you look at the employee table, SSN determines E name and SSN and P number determines hours, something like this. For example, if we consider the employee relation and if it has employee ID, employee name, and then the age, if I have employees 101, 102 and 103, if there is a functional dependency which says that employee ID determines employee name and age, here which is X component, employee ID is the X component and E name comma age is the Y component, and it clearly says that the values of E name or the values of age attribute are determined by the value for the column employee ID. That means if I have A, B and C are the names 28, 30 and 32, and if I have some other row where it has the value under column EID, if it is 101, since the functional dependency says that employee ID determines the attribute E name, so that is why if these two rows, when the value under the X component is same, they must also agree upon the Y component values. That is why here when if I have some other tuple with the same value, that is 101 under EID, let us not worry about whether it is a primary key or not. Let us, for the sake of understanding these functional dependencies, let us assume that if at all there is an other attribute which has same value under this employee ID, which is 101, and since according to this functional dependency which is laid down, that is employee ID determines employee name, according to this, both this is the X component, this is the Y component, and if two rows are having same value under X component, then they must also agree upon the value of the Y component, meaning that now I cannot have something else here. That means for 101 employee, the name cannot be K, because the functional dependency clearly says that 101 the name is A, so that is why it must be A. If it is not A, if it is something else, then this functional dependency does not hold. And similarly, if it is 101, the age must be, what should be the age? Age is 28. Similarly, here also the age must be same. That is the meaning of this functional dependencies, and then I can say that employee ID determines employee name or employee age. Otherwise, employee name is determined by employee ID. X functionally determines Y in a relation schema R if and only if whenever the two tuples in relation instance small r of the relation agree on their X values, they must also necessarily agree on their Y values. But Y determines X. When I say that employee ID determines E name, it is not same as employee name determines employee ID. That means here X determines Y. Okay, this is the functional dependency. It does not mean that Y determines X. It may be true or it may not be. True. Okay, that is why the other way is need not be true. FDs cannot be inferred. One important point to be noted is these functional dependencies cannot be inferred, because each and every functional dependency is going to capture some business rule. For example, the business rule says that the employee ID is unique and the employee ID is going to determine all other attributes of the employee table. So that is one business rule. Similarly, if I say that the company has a rule saying that all the employees working with a particular department will have the same salary. In that case, if I have employee table with employee ID, employee name, department number and then salary, then department number 10 for 101 the salary is 9K, and for 102 department number is equals to 20 and his salary is 10K. Suppose if somebody else employee with 103 and then whose department is 10, what must be the salary? Since there is a constraint which has been specified in the form of this functional dependency, which says that DNO determines the salary, and if two rows, if they are agreeing upon the value of X component, that is D number, then they must also agree upon the Y component value, that is salary. That is why this cannot be something and this must be 9K. That means these functional dependencies are there to capture the business rules or constraints. So that is why we must be we cannot infer the functional dependencies, rather it must be given by or defined by someone who knows the semantics of the database or the domain very well. They only can give this or define this functional dependencies. We cannot infer them. Diagrammatically, functional dependencies can be represented like this. Let us assume that there is a table called department or schema, relational schema department, which has attribute D name, D number, manager SSN, manager start date. So this is the relational schema, and then D number is the primary key. This functional dependency holds good for this relational schema. That is, the D number, which is primary key, determines all other attribute values, that is manager SSN, D name and then manager start. So how this can be represented diagrammatically? This can be represented like this, and this is how we represent a relational schema diagrammatically. A rectangle, and on the right hand top outside the rectangle we write the name of the relation, and then we divide the rectangle into compartments and then we write the attribute names which are associated with the relation. So, D name, D number, manager SSN, manager start date. D number is underlined because it is the primary key. Now, according to this functional dependency, it clearly says that D number determines D name, D number determines manager SSN, D number determines manager start date. So, how this can be diagrammatically represented? Like this: start a line which is starting or leaving from the X component, and then you draw a line and then make it an arrow, and which will point to the Y component attribute. Of course, in this particular case, on X side we have only one attribute, and on Y component we have three attribute. That's why we will start from D number and then take three arrows which will point to the remaining three attributes which are part of the Y component. Similarly, if you look at the works on table or works on relation, I have three attributes: ESSN, PNO and hours, and with the functional dependency available is, that is defined is ESSN comma P number determines hour. So, X component is ESSN comma P number and Y component is hours. That is why X and Y components, they may contain one single attribute or more than one attribute. It is possible, and this is how, because on the X component we have two attributes. That is why you underline these two attributes and start a line from there and then take it and make it to point to the hours attribute which is on the Y side. So, this is how we diagrammatically represent the functional dependencies. Then coming to the inference rules, which are very important concept in database design. If F, capital F, denotes a set of functional dependencies, we can infer or we can derive some new functional dependencies from specified FDs. Set of all possible functional dependencies is called as the closure of the functional dependency set F, and which is denoted by F closure. For example, let us assume that there is a relation R which has attributes SSN, ename, address, D number, and there is another attribute called as D name and then D location. The set of functional dependencies defined are, we denote it by capital F. The first functional dependency is SSN determines ename, address and D number. The second functional dependency is D number determines D name and D location. And if we assume that F denotes a set of functional dependencies, and using certain rules we can always infer some new valid functional dependencies. For example, if you look at the first functional dependency, I can write it as SSN determines ename, and I can also write it as SSN determines address, like this. So, SSN determines, because D number determines D name and D location, and D number is determined by SSN, there exists a transitive dependency. Then I can say that SSN can determine D number in turn it can determine D name and D location. Hence, I can infer that SSN can determine D name and then D location because of the transitivity. And similarly, SSN can determine SSN, which is called as a trivial dependency, where an attribute always determines itself. And similarly, here if you look at this, here X component has only one attribute, Y component has two attributes. Now I can split them and then decompose it and say and call it as D number determines D name, and similarly D number determines D location. Now if you carefully observe, from the set which contains only two functional dependencies, using certain rules I am able to derive or infer more number of valid functional dependencies. The original set is called as F, and if it contains some n number of functional dependencies, then by applying rules of inference or applying some rules, if I am able to derive some more number of functional dependencies called as M, then the union of this n plus m put together is called as F closure, which is called as the closure of the original functional dependency set capital F. This is called as F closure. Now, from a given set of functional dependencies, to infer or to derive more number of functional dependencies, we use some rules which are called as inference rules for functional dependencies. We have 6 important functional dependency rules, inference rules. The first one is called as IR1, then IR2, then IR3 up to IR6. And each one of these inference rules are based on some concept. The first inference rule IR1, it is not 1, it should be I. IR1 is actually based on reflexing feature or reflexing characteristic. That is, if I have a x component and if I have a y component, if x is superset of, this is superset actually, if x is superset of y, then I can say that x determines y. For example, if I have x component employee ID and then employee name, and on the other side I have employee name, then I can say that this always determines this, because the x component is superset of y component. That is why I can infer a new functional dependency wherein I can write that x determines y. That means if you have two sets x and y where x is superset of y, then you can write that x determines y. The second inference rule IR2 is known as augmentation rule. If you have a functional dependency x determines y, and then if you have a functional determinant, then we can augment x component and y component with the same attribute, then it gives rise to, or it gives a new functional dependency which is a valid functional dependency. For example, if you take this, on both the sides I am going to augment this with attribute z. So that is why here it is xz determines yz. Initially it was x determines z, and on both the sides I have augmented that with z. So that is why xg on x component and yg on y component, and this will become a new valid functional dependency. And the third one is called as transitive dependency. If I have x determines y and then if I have y determines z, then I can say that x determines z. This is transitive dependency. The fourth one is known as the decomposition rule or projective rule. If I have x determines yz, then I can say that x determines y and then x determines z. I am decomposing whatever is available on the right hand side, and then I am deriving or I am writing new functional dependencies. They are also valid. The fifth rule is known as union rule. If I have x determines a, and if I have x determines b, I can club them. That is, on x side, on right hand side, on left hand side, I have attribute x. On right hand side of these functional dependencies, I have a and b. Since LHS is same, then I can infer, I can write a new functional dependency where x determines ab, which is a new valid functional dependency. Again, if I apply the decomposition on this x determines ab, I can again get back x determines a and then x determines b. The sixth one is called as the pseudo transitive rule. When I have x determines a and then wy determines z, if these two are the given functional dependencies, I can always infer or derive a new functional dependency where it is wx determines z, which is a valid functional dependency. And if you carefully observe, if a functional dependency set capital F is given, and if we apply the first three functional dependencies, that is IR1, IR2 and IR3 repeatedly, I can always get the closure of the original functional dependency set, that is capital F, which is represented by this. And that is why the IR1 through IR3 are called as the Armstrong's inference rules. They are called as Armstrong's inference rules. And actually anything can be proved, any other inference rules, that is IR4, IR5 and IR6 can be proved in terms of IR1, IR2, IR3. That is why IR1 to IR3 are very, very important, which are called as Armstrong's inference rules. For instance, if you look at the sixth inference rule, what I have x determines y, and the second one is this one, wy determines z. How can I derive this? How can I infer this new functional dependency wx determines z? If you take the first one and then augment this with w on both the sides according to IR2. If I apply IR2 on this, which is augmentation, with augment both the sides with W, then what happens? This becomes Wx determines Wy. Now I have inferred this one. This is the originally given first one, originally given functional dependency second one. On applying IR2 on 1, that is functional dependency 1, I could get the functional dependency 3, which is nothing but Wx, that is augmenting both the sides with W, it is Wx gives Wy. Now on 3 and 2 it is transitive. So that is why if I apply IR3, I can say that because Wx determines Wy and then Wy determines Z. So now I can say that Wx determines Z, so which is same as this one. So that is why any other inference rule or inference can be derived using the first inference, first three inference rules, that is IR1, IR2 and IR3, that is reflexing, augmentation and transitive rules. These three are called as Armstrong inference rules. And these Armstrong inference rules are used, suppose if a functional dependency set F is given with FD1 and then FD2, then onto this set we can apply these Armstrong rules and then derive all possible new functional dependencies, and then that set of new functional dependencies plus the original one is called as F closure. Okay, closure of the functional dependency set F. Now we have a notion called as equivalence of sets of FDs. F covers E if every FD in E is in F closure. Suppose if I have a functional dependency set F and then another functional dependency set E, and I compute F closure and then I compute E closure, then if every functional dependency in E is available in F closure, then I can say that F covers E. And F and E are equal when F closure and then E closure are same. A set of functional dependencies F is minimal if it satisfies the following conditions. Every functional dependency in F has a single attribute for the RHS. That means in the functional dependency set F, every functional dependency has only one attribute on the right hand side, and the second condition is we cannot replace any functional dependency X determines A in F with any dependency Y determines A, where Y is proper subset of X and still have a set of dependencies that are equivalent to F. So then also it is not possible. That means in a set you should have all X components such that they are minimal. That is, removing any attribute from here will not hold, that is will not provide you the equivalent functional dependency set which is equivalent to original set. So that is the second condition. The third condition is we cannot remove any dependency from F and still have equivalent FDs to F. So if these three conditions are satisfied, then that FD set is called as minimal FD set. Now normalization. Now let us have a look at the normalization process. Normalization is first proposed by Raymond Boyce and Edgar Cord in 1972. What is normalization of data? It is the process of analyzing the relation schemas, and which is this concept is very specific to relational data model, and it is the process of analyzing the relation schemas based on their FDs and keys or primary keys. So these two concepts, that is the functional dependency concept and keys concept, are very important in normalization. So we analyze the relation schemas based on their FDs and for foreign key or primary keys, that is primary keys, to achieve the desirable properties, which are nothing but minimal redundancy and then minimal anomalies. Anomalies means undesirable properties, and the redundancy leads to inconsistency. That's why we need to eliminate redundancy, and at the same time we need to eliminate or avoid anomalies. And to achieve this, we analyze the relation schemas based on FDs and keys, okay, and perform some action to make those relation schemas more and more effective and then more and more perfect, so that there is no redundancy and the anomalies are eliminated from the schemas. And this process is called as this process of enhancing the quality of the relation schema is known as normalization process. It is based on functional dependencies and keys. In the process of normalization, unsatisfactory relations that do not meet required conditions or requirements are decomposed into smaller relations. Every level of normal form need to satisfy certain conditions. Suppose I have the various levels of normal forms: first normal form, second normal form, third normal form, BCNF normal form, fourth and fifth normal form. At every level, if I want to call my relation schema to be in a particular normal form, then it need to satisfy certain conditions. Let us assume that for normal form 1, the condition 1 to be satisfied. To be for a relation to be called in second normal form, it need to satisfy condition 1 and condition 2, that is the condition for first normal form as well as the specific condition that need to be satisfied for second normal form. Then this will also need to have C1, C2 and C3, that is this third normal form, so on and so forth. That means if I say that my relation schema is in BCNF normal form, it means that it satisfies all the conditions that have been laid down for that particular normal form, and it is also assumed that it is the meaning is also that that particular relation schema is also in all the lower normal forms. That is, if I say that my relation schema is in BCNF normal form, it also means that it is in 3NF, it is in 2NF and it is in 1NF. So that is why for every normal form, a relation to be called in a particular highest normal form, it need to satisfy certain conditions, and normal form of a relation refers to the highest normal form condition that it satisfies. And suppose there is a relation R and it satisfies first normal form condition, second normal form condition and third normal form condition. It does not satisfy the BCNF conditions and fourth and fifth, then the highest normal form satisfied is the third normal form. Then I can say that my relation schema is in third normal form. Similarly, if I have a database schema or a database which has relations R1, R2 and R3, if R1 is in second normal form, R2 is in third normal form and R2 is in 1NF, then I can say that the highest normal form satisfied by the database itself is going to be 1NF, because if I want to call, if the database need to be called in third normal form, all the minimum normal form, highest normal form that is satisfied by all the relations is 3NF. But in this particular case, all the normal forms, all the relations, they satisfy first normal form, but the R2 is in first normal form, R2 is in 3, R1 is in a second normal form. So that is why this is R3, R3 is in 1NF, R2 is in 3NF, and I assume that R1 is in second NF. So what is the common factor? All the relations are definitely in 1NF, and R1 and R2 are in 2NF, R2 alone is in 3NF. So that is, what is the normal form satisfied by all the relations? It is 1NF. So that is why I can call the database to be in, I can say that the database is in 1NF independently. R1 is in 2NF, R2 is in 3NF, R3 is in 1NF. So that is the concept of normal forms. Now schema refinement, sometimes which is also called as database design, encompasses two activities: normalization activity and then checking for other desirable properties like lossless join property and dependency preserving property. Normalization is bringing the database to the required or desired level of normal form, okay, and we use functional dependencies and keys. Then checking for other desirable properties are, that is, in the process of normalization, suppose let us assume that I have a relation schema R, it is in 2NF. Due to some reasons or the requirements, I am not satisfied with this normal form, I would like to take the relation to 3NF. In this process, I will decompose R into R1 and R2 using certain principles, and now R2 and R1 are in 3NF. Then my database is in 3NF. So in this process, we adopt decomposition. We resort to decomposition. When we split or decompose a bigger relation into smaller ones, I need to take care of certain desirable properties. My decomposition must be lossless join decomposition, and my decomposition must be dependency preserving decomposition. Then only it is desirable. That is why when you decompose a bigger relation into smaller ones, we also need to check for some desirable properties. In this schema refinement activity, or database design activity, we take care of two things, that is normalization and checking for desirable properties at the time of decomposition. The above properties are desirable during the process of decomposition. Some definitions useful in understanding database design are key. It is a minimal super key, which is also called as a candidate key. All minimal super keys are called as candidate key, and one of these candidate keys will become a primary key and other candidates keys of the relation will become alternate keys. Let us assume that a relation can have any number of candidate keys. What is a candidate key? Candidate key is a minimal super key. That means if I have a super key like this, employee ID comma employee name determines department number. Actually, to determine the department number, employee ID is alone, it is spurious. So that is why I eliminate this. The previous case where I had employee ID and employee number, employee name, which is not a minimal key, minimal super key, because it contains two attributes. Actually, two attributes are not required to unique identification or to determine this particular attribute value. Otherwise, if you look at the employee database as a simple example, employee database, employee ID, employee name, SSN and salary, and let us assume that using this I can uniquely identify all these things, and using SSN also I can uniquely identify all these things. So what is a super key? Employee ID comma employee name, this also can uniquely identify a tuple in the relation, so it is a super key. And similarly, employee ID comma salary can also uniquely identify tuples in the relation, hence this is also a super key, but they are not minimal super keys. Minimal super key means what? If you take a super key and eliminate a attribute, still it is able to identify a tuple uniquely, then it is not minimal. So in this case, if I eliminate salary, still this attribute alone can identify or uniquely identify rows or tuples in the employee table. So this is in the earlier case, EID comma ename is not minimal. Now after elimination of this, this is minimal, this has become minimal. So that is why all minimal super keys are called as candidate keys. Candidate keys are keys which provide unique identification of the entities or rows in a given relation. For this employee table, employee ID is one candidate key and minimal super key, and SSN is also another minimal super key. All minimal super keys are called as candidate keys, and out of these candidate keys, one will become the primary key and remaining candidate keys will become alternate keys. In this example, let us assume that I have chosen to go with the employee ID and then made it as the primary key, then the other available candidate key, which is SSN, that becomes alternate key. We study the general definitions of normal form in terms of keys, not just in terms of primary keys. Suppose some textbooks, they describe us or give definitions for normal forms in terms of primary keys, and the more generic way of doing it is considering all the keys, that means considering all the candidate keys. In this discussion, we are going to define the normal forms using all or in terms of all candidate keys available for a given relation schema. Let us start discussing about the normal forms. The first one is 1NF, that is first normal form. It states that domain of any attribute must include only atomic, that means single, simple, individual values. That means it cannot be multi-valued attribute or it cannot be a complex attribute. Let us have a look at this example. The table's name is department. If you look at this, it contains 3 columns and 2 rows. For the first row, department ID is equals to 10, department name is equals to engineering, but it is located at 2 locations, Hyderabad and then Chennai. That means this particular row, that is row 1 R1, for column D location has multiple values. The multiple values are not allowed according to the relational model. The first normal form says that under any column for any row in a table, the values must be single, simple and individual. It cannot be multiple values or it cannot be a complex value. So that is why this is not in first normal form. To bring it to first normal form, what I can do? I can apply this technique. Just make it a separate row, make it another row, then copy it here, 10, engineering, 20, marketing. Yeah. After this modification, if you carefully observe, if you look at any row under any column, it has only single value or simple value. It is not complex or it is not multiple values. So that is why this is in 1NF, wherein in the previous case that example was in not even in first normal form. From now onwards, we assume that whatever relation we talk about, by default it is in 1NF, because if it is in 1NF, then only it is in relational model according to relational model philosophy. So that is why we assume that all relations, they will be by default in first normal form. They will satisfy this condition, that is any attribute, it will include only the single, simple or individual value. That is our assumption. Then we talk about the second normal form. It is based on full functional dependency. If you have a functional dependency X determines A, we can say that A is fully functional, the dependency X determines A is fully functional if we remove any attribute from X component, the FD does not hold anymore. For example, all non-key attributes are fully functionally dependent on key, or otherwise we can say that no non-key attribute should be dependent on part of the key or partially dependent on the key. Suppose if you take this example, this is the definition of the second normal form, condition for the second normal form. It says that all non-key attributes must be fully functionally dependent on the key. It could be any key, need not be a primary key. For example, a table may contain more than one candidate key, and we need to consider all these candidate keys to look for the second normal form condition. Otherwise, it says that no non-key attribute is partially dependent on the key. If you look at this relation, employee relation, which has employee ID, pnum, hours, ename and p-location. And here, since I have this combination of employee ID and pnum is going to determine all other attributes like this. This is the FD1 given and this is the FD2 given. So FD1 says that employee ID, comma, pnum together determines hours, ename and p-location. Second one is employee ID alone can determine ename, comma, only ename. And the next functional dependency says that pnum alone can determine p-location. So if these are the FDs given, there are three FDs given, FD1, FD2 and FD3. What becomes the key? If a set of attribute or a single attribute, if it can determine all other attributes, that becomes a key. What becomes key for this particular relation? If EID alone, it cannot become key, because using EID alone I can determine only ename. Pnum alone cannot become the key, because using pnum alone I can determine only p-location. But combination of employee ID and pnum can become or can determine hours, ename and p-location. If a set of attributes or a single attribute can determine all other attributes, then it can be called as a key. So that is why for this relation EID, the combination of EID and pnum becomes the key. Now let us check whether it is in 1NF or not. We assume that all the relations what we are going to check from now onwards, by default they are in first normal form. Let us check for whether it is satisfying the second normal form condition or not. And if you take any functional dependency and then any non-key attribute, specifically any non-key attribute, what are the key attributes? EID and pnum are the key attributes, and hours, these are the key attributes, and then hours, ename and p-location are not key attributes, they are called as non-key attributes. And the second normal form says that all non-key attributes must be completely dependent on the key, no partial dependency of a non-key attribute on the part of the key. Okay, and this violates, suppose if you take hours, hours is completely dependent, this attribute is completely determined by the key, there is no problem. But if you look at this one, employee ID determines ename functional dependency, ename is a non-key attribute. EID is what? EID is a key attribute, but it is not complete key, it is part of the key. So that is why ename is a non-key attribute which is dependent on part of the key. Then I can say that there exists a partial dependency in this relation. A non-key attribute is partly determined by part of the key. There exists a partial dependency. Hence, I can say that this is not in second normal form. And one more reason why I have said that it is not in second normal form is, if you take the other functional dependency wherein the pnum determines p location. P location is a non-key attribute, but pnum is a key attribute, but it is part of the key, it is not the complete key. Then I can say that the non-key attribute p location is determined by part of the key. Hence, this functional dependency and this functional dependency, they are not obeying the rule for second normal form. It is why they are violating second normal form condition. Hence, I can say that it is not in second normal form. The highest normal form satisfied is only the 1 NF. Okay, this is how we can decide the highest normal form of a given relation. Then, in a process to bring it to the second normal form, we perform decomposition. If you look at this, in the previous case, now what I will do is, I will put EID determines ename. Now, I will take EID and ename attributes and then put it in a decomposed relation, separate relation, and then similarly pnum determines p location. I will put pnum and p location in another table, and then remaining other things will be in the third table. So, this is called as decomposition. The single employee table is now decomposed into 3 relations, that is relation 1, relation 2 and then relation 3. Now, the functional dependencies which are violating the second normal form condition, okay, and we will make union of x and y and put them in one single relation. So, EID determines ename, that was the functional dependency which was violating second normal form condition. So, that is why this is the x component, this is the y component. I have taken both of them together and put them in relation R1. So, this is the first relation R1. Next, pnum determines p location, that also violated second normal form condition. Make union of x and y and put it in separate relation R2. And for this R1, EID determines ename, there is no problem. This is the only one functional dependency available, there is no partial dependency, hence this is in second normal form, there is no problem. And this is also in second normal form. And what are remaining? Employee ID and pnum and hours, I am putting them in the third relation. And what is the key for this? Employee ID and pnum alone can determine hours, this becomes the key. Now, the non-key attribute hours is completely determined by the complete key, that is EID comma pnum. So, hours is a non-key attribute and there is no partial dependency of that on the key. So, that is why it is in second normal form. Now, after decomposition of employee table into R1, R2 and R3 and individually, independently, all of them are satisfying the second normal form condition. Hence, I can with confidence can say that this given database, now earlier the database has only one relation. Now, after decomposition, there are 3 relations available in the database and all the relations are satisfying second normal form condition, and that is the highest normal form satisfied by all the relations in the database. Hence, the given database is in second normal form, it is in second normal form. So, when a relation is given with attributes and a set of functional dependencies are given, first we need to identify the keys, then we need to check for the satisfaction or satisfying the highest normal form condition and declare what is the highest normal form condition. For example, let us assume that there is a relation called R which has A, B, C and D as the attributes, and A determines B and B determines D. A determines C and B determines D. These are the functional dependencies. Given this kind of situation, first we need to identify the key. What is a key? The definition of a key is a single attribute or combination of attributes which can determine all other attributes will become the key. The key provides unique identification to the entities in the or the rows or tuples in the relation. A alone cannot become key, B alone cannot become key, and C and D anyway they cannot become keys. But put together A and B, A can determine C, B can determine D. So A and B can determine AB and they can also determine C and it can also determine D. So that is why the key for the given relation is A comma B. Now having identified the key, now check whether it is in second normal form or not. If you take the functional dependency AB determines C, AB determines C, that is because AB is the key. By default, key determines all other attributes. Similarly, AB determines D, and similarly, what is the other original functional dependencies given? A determines C and B determines D. Now, if you look at this, AB determines D, X component and then Y component is a non-key attribute and it is completely determined by key. Yes, it is in second normal form. If you look at AB determines C, C is a non-key attribute and it is completely determined by the complete key. So hence it is also in second normal form. But if you look at the third functional dependency, A determines C, C is a non-key attribute but it is determined by A, which is only part of the key, which is not a complete key. Hence it is violating the second normal form condition. And the third one is also D is a non-key attribute but B is part of the key, it is only a partial part of the key, hence the partial dependency exists. This also violating the second normal form condition. Hence the highest normal form satisfied by this relation is 1NF alone, only 1NF. I can perform decomposition, that means take the functional dependencies which are violating the second normal form condition, make union of X and Y components, put them in a separate relation. So I will create R1 where I will put A and C. I will take R2 and then I will put B and D, and the remaining things A and B will be in the original relation, that is R3. Now for this A is the key, for this B is the key, for this AB is the key. So now if you individually look at these relations, they are definitely in second normal form. Initially I had only one relation, after decomposition I have 3 relations. So that is why now the database which contains 3 relations is in second normal form. Since all the highest normal form satisfied by all the component relations of this database are in second normal form, hence the database is in second normal form. So we have seen what is the schema refinement process, which is also called as database design, and what is functional dependencies, and what are the inference rules, and what is normalization, process of normalization, and we have discussed about 1NF and then 2NF conditions. In the next class we will discuss about the remaining normal forms 3NF, BCNF and other normal forms, and we will also look at the desirable properties, how to check whether a decomposition is maintaining the desirable properties or not. That is, the decomposition must be a lossless joint decomposition and it must be a dependency preserving decomposition. And after decomposing a relation R into R1 and R2, how to check whether this decomposition preserves or contain the desirable properties or not. That we will discuss in the next class. Let us stop here. Thank you very much.